events that have deeply engraved into the memory of many Luxembourgers are the devastating flash floods that have occurred in the east of the country in 2016 and 2018. The damages were high, including flooded houses as well as washed away bridges and streets. The water levels of what normally are small streams were beyond the residents' memories. Ever since, flooding following thunderstorms seems to regularly occur across the country. Where do I have to point? Flash floods are devastating floods that are following thunderstorm with high rainfall intensities, especially during the summer. While they've been a known phenomenon in dry and Mediterranean regions of the world, they've been increasingly observed here in Central Europe, where previously slowly developing floods during winter have dominated the flood regime. Now, we want to understand why there has been this change in flood characteristics. Therefore, we've collected data on atmospheric parameters and analyzed the atmospheric conditions during thunderstorm events of extreme rainfall that have the potential to trigger flash floods. These atmospheric conditions can be broken down into three criteria to form a thunderstorm. The first is atmospheric instability, that is high enough that air masses can rise the convection to form a thunderstorm cloud. The second is a high moisture content of the atmosphere. Without a lot of moisture, there cannot be enough rainfall to trigger flooding. And the third is a slow motion of the thunderstorm cells. In this region, it's especially the slowly moving thunderstorm cells that have enough time to dump the entire rainfall load over one specific area to trigger flooding. For each of these three categories, we have analyzed proxy parameters from climate reanalysis data, such as the potential energy for convection, the specific moisture of the atmosphere, or wind speeds and shear winds. Based on these, we've conducted trend analysis over the past 40 years and found that the instability has increased in the study area. The moisture contents of the atmosphere have significantly increased throughout the entire study area, both in absolute values as well as in the frequency of occurrence of high enough values for extreme precipitation. The slow motion, so the wind speeds, have rather stayed unchanged. However, these three in combination lead us to the conclusion that atmospheric conditions favoring thunderstorms did become likelier. On this map, you can see that over the French part of the study area, the trend is neutral or slightly negative. However, over Luxembourg and the southwestern part of Germany, the atmospheric conditions favoring thunderstorm events with extreme rainfall have increased by a few hours every year over the past 40 years, which leads us to a few more days with the potential to trigger flooding. These results are especially significant in the northeast of the study area and along the southern border of Germany. In the next step, we would like to use these findings to better understand why simulating and forecasting flash floods is so difficult. So far, standard hydrological conceptual models have been used where you give as input data some rainfall, temperature, or evaporation, and with some parameters and calibration, you get a discharge. However, we would like to include also the atmospheric parameters just analyzed and use a machine learning approach to get out all the information we can from the data we have. And based on these, we hope to learn something from the data which we can then use to analyze the standard models to understand why they're having difficulties in simulating the flash floods. With my approaches and analyses, I hope to contribute to a better understanding of extreme rainfall and flash flood events, and therewith contribute to help decision makers in finding climate-adjusted solutions. I'll be happy to further discuss with you about extreme rainfall and flash flood events later. Thank you.